Okay, so we're going to move into the generation of CP time profiles. We're going to use the same data set of 2000 compounds that we've used before. So I'm going to load it right now. And we're also going to calculate physical chemical properties for these compounds. Now, that is not something that's absolutely necessary, but it is useful in terms of the further analysis capabilities that this will give you downstream. However, HTPK can run and perform these calculations behind the scenes as part of the HTPK simulation itself. So the way you access the CP time profile functionality is either under Tools, PK Simulation, and CP time curve over here, or as this icon in the icon bar. Now notice that these are currently grayed out. It's because I don't have any compounds selected. So you need to have at least one or multiple compounds selected in order to trigger this calculation. So let's say we select compounds 4, 5, and 6, go to our CP time profile icon, and as we've seen before, we have the choice between two physiologies, human and rat. You can't run both simulations simultaneously, one or the other, so you can run one and then the other one afterwards. And then in terms of dosage form, you have immediate release tablet or IV bolus. Similarly, you can't run those simultaneously. Now, in terms of doses, you can run multiple doses simultaneously. So if you wanted to generate CP time profiles for, say, 1 and 100 milligram doses, you could very simply do so by entering 1 semicolon 100 and run the simulation. So it's a very simple process to do. We're just going to do it with a default 10 milligram dose and simply hit the run button, and the software will generate your CP time profile. So this is our CP time profile. Now notice that we have our 3 compounds in 3 different colors identified by the compound IDs. And now if you click on each one of these, you will see the PK parameters appear in this window outlined here. And of course, they are different for each compound. So if you select the red curve, the red compound, then you get this outline in red. Same thing for the third compound in green, etc. So again, very access to the PK parameters that way. So say we want to jump to a different compound now. So we want to generate a CP time curve for compound 3. We would go through the same process, hit our CP time curve icon, and now instead of going for a single dose interval, say we want to have 5 dose intervals for this compound. Of course, we can run that very simply and generate this CP time curve. Okay. Now, we have access to interesting functionality in terms of simulating what the effect of certain physical-chemical properties are on our CP time curve. And in order to do so, we can go back to our CP time curve setup panel and modify certain parameters. And it's very handy, actually, to overlay future curves onto this one. So we're going to select the previous curve we just obtained and then overlay our future curves on this. So we're going to go to the advanced panel here, and as I've mentioned before, the HTPK simulation uses a certain number of physical chemical properties that are being calculated behind the scenes, and these are the models that are used in this process. Now you can actually see and import in these panels what the corresponding values are for solubility, permeability, etc. And you can do so very simply by pressing this button over here, this right pointing arrow. Okay, so, and that is why we calculated those physical-chemical properties ahead of time, is it gives us the ability to import these parameters into this panel. Okay, and now we may be interested in investigating the situation where, say, the solubility is not as high as what was predicted by the model. So right now, our solubility model, S plus SW, solubility in pure water, is predicting a solubility of 1.9 mg per ml. And we may be tempted to ask the question, well, what would be the effect on the CP time curve if the solubility was less than that? Say, what if it were only half a mg per ml? How would that affect our CP time curve? And it's very easy to do. Just hit the run button again, and it will perform the simulation with the adjusted parameter. And then you see that it is predicting that there would probably not be a very significant effect, if any at all, on our CP time curve. And this may be a situation that we've seen before. For example, if this compound happens to be permeability limited, then probably solubility being different would not have a very significant effect on the pharmacokinetics of this compound. And of course, this is a hypothesis that we can test for. If we go back to our CP time curve panel here, we're still going to overlay on this curve, go back to our advanced panel. Now we're going to restore the solubility that came from our model very simply by bringing it back in. And now let's investigate, say, the effect of permeability. So our permeability model is predicting a value of 2.2. Say we can investigate what if it was only, say, 1.2, for example. How would that affect the CP time curve? Again, it's just a very simple scenario to investigate. Let's run the simulation again, and we see that we reach Cmax values in our CP time profiles that are somewhat lower than what we reached under the previous assumption. So that gives you the sense of how you can investigate the effect of certain parameters on the CP time curve. And you can also, of course, these don't necessarily have to be simulated values. They can also be experimental values. So if you have experimental data for any of these parameters, you can enter them and have a finer simulation than if you were to run, say, all in silico, for example. So anyway, I hope that was useful. And we will now jump to our next part on dose calculations. Okay, so we're getting to one of our last topics here, which is dose calculations. And that is accessed under Tools, PK Simulation, Dose Estimation, or through this pill-shaped icon over here at the top. So if you click on this, you can trigger this calculation either for a set of selected molecules or the entire set of molecules in your spreadsheet. And just as we've seen before, you have just the choice of human or rat physiology, one or the other, and also the choice of dosage form, either immediate release tablet or IV bolus. Okay. So, and what the software will do is that for each molecule, it will calculate the dose that is projected to be required to reach a certain target plasma concentration at steady state. So for example, if we wanted to reach a target plasma concentration of 0.1 micromolar for all of the compounds in this list, we would select micromolar over here and then enter 0.1 micromolar. Okay. Now, one of the things that can happen is that you don't necessarily want to shoot for the same target concentration for all of the compounds in this table. For example, if you had an IC50 value and you wanted to calculate the estimated dose so that the projected concentration would never drop below that IC50, what you would do is over here, instead of entering a fixed value, you would point target concentration to a column containing your IC50. Okay. And then instead of optimizing against C average, you would optimize, for example, against C min. Okay, so in this case, you would always be above C min. So you have a choice in target functions here to be optimized, C average being area under the curve divided by the time interval, C min and C max. So you've got three possible values to optimize against. So the most common situation is going to be C average. And let's go back to our first hypothesis here, which is that we would like to project a dose estimate, the projected dose to reach a target plasma concentration of 0.1 micromolar at steady state. So we would enter 0.1 here, okay, and then perform this calculation. Now the software needs an initial dosage guess as a starting point to perform the optimization, and you can leave 10 milligram as the initial dosage guess here, and then basically go and run this calculation, and we have 10,000 compounds here. So realize here that it is performing an optimization for each molecule. That is the number of dose intervals that is required to reach a steady state will usually be different for each molecule. So it needs to figure that as part of the optimization work that it's doing. And then it needs to perform the back calculation of the dose, starting with the initial guess of 10 milligram, and then optimize that to reach the target concentration here of 0.1 micromolar at steady state. So it's really doing a lot of work here. This process is actually multi-threaded, so it's running on this particular computer, which is just a regular laptop. It's running on 7 threads. Okay. And so it is outputting for us some interesting parameters. So the main one that's going to be of interest to us is this opt dose underscore HUM for human, okay, and dash 0.1 because it's 0.1 micromolar. And that is the projected dose that is required to reach the specified concentration at steady state, which again in this case is 0.1 micromolar. The other parameter of pretty high interest would be the T1/2 or T half SS underscore HUM. That is the estimated half-life in hours at steady state in the selected species for that optimized dose level. Okay. And then there is the dose count SS underscore HUM, which is the number of doses that is required to reach steady state at that optimized dose. So again, that's going to be different for each compound. In this first compound, it's 3, and this one it's 4, and this one it's 21. It really depends on the PK parameters for that molecule. So hopefully that give us a pretty good sense of how you can perform these dose optimization, dose calculations within the HTPK simulation module. Okay, so our last topic for the day is the advanced settings and parameter files for the software. So we expose a number of options through the user interface, but there are certain advanced options that can only be accessed through files. And well, the reason is if we really exposed every possible parameter, it would really make the user interface pretty complicated. So we need to draw the line somewhere. And again, there are a lot of things you can adjust in the UI, and then at the next level, you can dive into files if you want to access sort of a higher level of detail. So, for example, this we have this file here, acat.inp. This file contains the physiological parameters which are used to run the ACAT model, and that's the Simulations Plus Advanced Compartmental and Transit model. That is the same approach that is used in the GastroPlus software. So there's actually two sister files. There is an acat.inp, that's the human that's the file for the human setup, and there is also a rat acat.inp, and that's, as the name suggests, that contains the parameters for the rat species. And so these are text files which you can open and potentially modify if you desire to access these parameters. And so the file describes what the different parameters are and also gives you the option to the possibility to modify them if you desire to do so. Okay. Then there are also two other files, well, there's several other files. There is a sim RIA and a sim ria.hia and a simhia.hia. These are the formulation parameters. So these contain dose volume, particle size, etc. So notice that the files pretty much always go in pair. This is they go in pairs. The first one, this simhia, that's the file for the human physiology, and this RIA is the file for the rat physiology. So again, there are a lot of things you can do by a lot of additional things that you can do by modifying these files. Again, here it provides a description for each of the parameters that are involved in the simulation. The formulation parameters, and then later down in the file you have the ability to modify these parameters if you so desire. One quick word of caution: if you are going to modify these files for a specific purpose, we strongly encourage that you do so in your local directory, or at least minimally safeguard a copy of the original file so that you can go back to it. So there's a lot of meat on the bone here. I hope that was useful. I'm going to stop here and thank you for your attention.